All right, so good afternoon, everyone, and welcome to the UH Energy Electric Vehicle webinar series. In this webinar, we will be discussing optimizing the energy usage of electric vehicles and internal combustion electric vehicles in public transportation with Dr. Aron Laszka. My name is Andreas Bryan, and I'm a biomedical engineering student at the University of Houston, and I will be the moderator for today's event. So before we begin with the event for today, I want to take a minute to thank our partner, Evolve Houston. We're so glad to have them working with us to help provide Houstonians with reliable alternatives for transportation. I'd like to take a moment to remind everyone of our next webinar in this series. It will take place on December 10th and will address next generation batteries for electric vehicles and stationary storage. Our speaker will be Dr. Yan Yao, who is a professor in the Department of Electrical and Computer Engineering at the University of Houston. To learn more about the electric vehicle webinar series and other UH related projects, please visit the UH Energy page using the link in the PowerPoint. So moving forward, we will have the Q&A session at the end of the presentation, so please hold on to your questions until the end. That being said, we will be utilizing the chat function, so when the time comes for the Q&A session, go ahead and submit your questions in the chat, and I will be able to moderate the incoming questions in the order they are received. So without further ado, I would like to introduce Dr. Aron Laszka. Dr. Laszka is an assistant professor at the University of Houston in the Department of Computer Science. Some of his research interests include cyber-physical systems, smart and connected communities, cybersecurity, applications of artificial intelligence, machine learning, and data science. He has groundbreaking work published in top-tier AI and CPS conferences, which include AAAI and ICCPS. Some of his research projects have been recently funded by the NSF, DOE, DHS, and Siemens. Before being a part of the University of Houston community, Dr. Laszka had many important roles. He was a research assistant professor at Vanderbilt University from 2016 to 2017, a postdoctoral scholar at the University of California, Berkeley from 2015 to 2016, and a postdoctoral research scholar at Vanderbilt University from 2014 to 2015. He graduated summa cum laude with a PhD in computer science from the Budapest University of Technology and Economics in 2014, and in 2013, he was a visiting research scholar at the Pennsylvania State University. In this webinar, Dr. Laszka will be presenting findings from his Department of Energy funded project on the development of a data capture and analysis framework to improve the operational planning of regional transportation authorities. He will discuss how high-resolution data can be collected from a fleet of electric and internal combustion engine vehicles and how this data can be integrated with traffic, weather, and other features to create contextualized energy usage predictors. As a result, this can be used by public transportation authorities across the nation for operational optimization. He will present experimental results based on data collected from the vehicle fleet of the Chattanooga Area Regional Transportation Authority, one of the project partners. So without further ado, the presentation will begin shortly.
Welcome, everyone. My name is Aron Laszka, and I'm an assistant professor in the Department of Computer Science at the University of Houston. In this talk, I will present the results of an ongoing research project whose goal is to help public transit agencies to reduce operational costs and environmental impact of electric and internal combustion engine transit vehicles through predictive analytics and operational optimization. I would like to begin by emphasizing how public transit could play a key role in reducing energy consumption. Currently, transportation accounts for 28% of the total energy used in the United States, and as such, it is responsible for immense environmental impact, including urban air pollution and greenhouse gas emissions, and could pose a threat to energy security. Since a major part of this usage is due to personal vehicles, switching from personal vehicles to public transit systems could significantly reduce energy use and hence environmental impact. However, even public transit systems require substantial amounts of energy. For example, bus services in the United States are responsible for at least 19.7 million tons of CO2 emission annually. And in sparsely populated areas, the efficiency of public transit can be extremely low when measured in energy per passenger per mile. So the question is, how can we make public transit systems more energy efficient? And of course, one possible approach is the adoption of electric vehicles. Electric vehicles can have much lower energy costs and environmental impact during operation than comparable internal combustion engine vehicles, especially in urban areas. Unfortunately, electric vehicles are also much more expensive than internal combustion engine vehicles. Typically, diesel transit buses cost less than $500K, while electric ones cost more than $700K, or close to around $1 million with charging infrastructure. As a result, many public transit agencies can afford only mixed fleets of transit vehicles, which consist of electric vehicles, hybrids, and traditional internal combustion engine vehicles. Transit agencies that operate such mixed fleets of vehicles face challenging operational optimization problems. These agencies need to decide which vehicles are assigned to serving which transit trips, when electric vehicles are scheduled for charging, and how transit trips are scheduled and routing, considering the characteristics of a diverse fleet of vehicles. Since the advantage of electric vehicles over internal combustion vehicles varies depending on the route and time of day, these decisions can have a significant impact on energy use and hence on environmental impact. For instance, the advantage of electric vehicles is much higher in slower traffic with frequent stops and lower on highways. The HTML project aims to help transit agencies with these operational optimization problems by developing a novel framework for data collection, storage, and processing, machine learning-based predictors of energy use, and efficient optimization algorithms. This project is funded by the US Department of Energy, and it is a collaboration between multiple universities, including the University of Houston, Vanderbilt University, and the University of South Carolina. In this talk, I will give an overview of key results, but I also encourage you to visit our website, smarttransit.ai, where you can find more details, datasets, software, publications, and information on related projects involving our team. A key advantage of our project is that this is led by a public transit agency, the Chattanooga Area Regional Transportation Authority, or CARTA for short. CARTA is responsible for operating a multimodal public transit system in Chattanooga, Tennessee, serving over 3 million passenger trips per year, with 17 fixed routes, 3 dial-a-ride demand-responsive routes, and a complementary paratransit service. CARTA operates a range of vehicles, including gasoline, diesel, hybrid, and a growing battery electric fleet in a variety of lengths, sizes, passenger capacities, ultimately spending more than $1.1 million on fuel annually. In this talk, I will first describe our framework for collecting, storing, and analyzing data from CARTA's fleet of vehicles. Second, I will show how we use the data to train machine learning-based predictors of transit energy usage. Then, I will present our algorithms for transit optimization, which build on these energy predictors. Afterwards, I will give a brief overview of a couple of other interesting outcomes of this project. And finally, I will highlight some related projects from our team focusing on transportation and energy. So let's begin with an overview of our data collection and storage framework. Our primary goal is to optimize energy efficiency, which is directly correlated to the cost of operation. As I mentioned before, CARTA operates a mix of aging diesel buses, diesel hybrids, and newer BYD battery electric vehicles with wireless inductive charging capability, in addition to gasoline-powered vans and battery electric shuttles. The premise of this research project is that significant energy savings are possible if we optimally assign a schedule the vehicles from a mixed transit fleet consisting of electric, hybrid, and internal combustion vehicles. To validate this hypothesis and to perform the optimization, we needed to collect high-resolution data sets that will tell us how a given vehicle performs during operation, even as exogenous temporal features such as traffic and weather change. Therefore, we worked with a vendor to integrate telemetry sensors into each transit vehicle through J1939 and OBD2 ports, and we designed an architecture that will collect this data at a high resolution, meaning at 1 Hertz or more. With this data, we can use machine learning to train predictors that can estimate the energy consumption of different vehicle types on different routes and under varied conditions. Our project utilizes a number of data sources which provide information on the vehicles, passengers, traffic and road conditions, weather, and so on. In addition to the problem of having the right data available at the right place, our team and other urban science researchers also have to deal with the inefficiencies of querying and operating on high volume and high velocity geospatial data. For example, in the project, we collect vehicle telemetry data from various sensors, vehicle locations, occupancy, and route delays from clever devices, traffic data from heat maps, and weather data from dark sky. Our innovation is to build a distributed data store that is centered around the concept of a distributed ledger layer, in which each data source is assigned a topic. As the velocity and volume of each topic is highly variable, each ledger is then distributed across multiple nodes aligned for horizontal scalability at the topic level. The append-only structure also enables real-time temporal synchronization between data streams by using interpolation features. Structured data views are derived from the distributed ledger and can be used for analytical queries that can sustain latency. The structured views can attach to multiple topics and through processing can therefore be used to integrate external static data sources such as OpenStreetMaps or weather data with real-time transit telemetry data. These views can also be used for machine learning algorithms, which I will discuss later. Here you can see the details of our current implementation of the proposed architecture, which is currently running on a private cloud at one of our partner universities. Note that this data collection, storage, and processing framework could be easily adopted to other transit agencies. It is not specific to CARTA. As an immediate benefit, this data framework enables us to provide CARTA with historical, real-time, and predictive analytics. Here you can see some examples taken from an online visualization dashboard. You can actually check out the public online version of this visualization dashboard at smarttransit.ai/energy dashboard. If you do, please know that it may take a couple seconds for the dashboard to load. It's not an error, just give it a couple of seconds. The first example of long-term structured analysis that we were able to do with our data store is shown on this slide. The figure on the left shows the energy consumption in kilowatt hours per mile for electric vehicles as collected between December 2019 and April 2020. As you can see, there is a variance in efficiency across the different routes, which are shown on the horizontal axis. The figure on the right shows the same variance for diesel vehicles. To compute these values, we integrated the fuel rate across the trip for the vehicle and then used the standard conversion values for diesel fuel from Energy Information Administration. While it is clear that electric vehicles are more efficient, the question remains that if there are a limited number of vehicles available, then which trips should be assigned to the electric vehicles? To further investigate this question, we started looking at the correlation with exogenous features such as time of day and weather. These figures show the energy used as kilowatt hour per mile for electric vehicles and for diesel vehicles. On the horizontal axis, you can see the different routes on which these vehicles drive, while the vertical axis shows the different times of the day. As you can see, the diesel vehicles on Route 21 are more affected by the time of day, you can see this in the figure on the right, than electric vehicles. The time of day is a good surrogate for traffic, and hence we can conclude that diesel vehicles are likely more sensitive to traffic. Please note that the figures are on different scale. The scale is actually much higher for diesel vehicles. Based on these findings, we formulate the hypothesis that we might want to assign more electric vehicles to trips that will occur on routes with heavy traffic congestion. Similarly, we can also see a correlation between vehicle energy consumption and various weather factors. In these figures, the horizontal axis show different times of the day, while the vertical axis show different weather features. The plotted values are correlation values between these weather features and the energy consumption of electric vehicles on the left and diesel vehicles on the right. So you can see this is a complex nonlinear relationship. Although not shown, we have also determined the impact of other factors such as elevation changes on the energy consumption. In addition to analyzing historical data, we also provide predictive analytics to help CARTA and other transit agencies with the planning of their operations. Please recall that our primary goal is to enable transit agencies to minimize their energy use through operational optimization, including vehicle routing and scheduling. To perform such optimization for mixed fleets of diesel, electric, and hybrid vehicles, agencies must be able to predict how much energy a vehicle would use on a given route at a given time, even if no data has been collected for that particular combination of vehicle model and route. Otherwise, we would not be able to evaluate new planned assignments that include new combinations of vehicle models and routes. This would restrict our optimization to only combinations that have already been tried in the past. To address this need, we provide macroscopic energy predictors based on state-of-the-art machine learning techniques, such as deep neural networks, and based on the data collected in this project. These predictors are ideal for planning purposes since they require us input only static features that are known ahead, such as the model of the vehicle, the route to be taken, and the time of day, as well as features that can be forecasted, such as expected weather and traffic conditions. Before we can apply machine learning models, we need to perform a number of data cleaning and preparation steps. Our workflow starts with vehicle telemetry data recorded from Veracity, which we can retrieve from our data storage framework. To join this data with other sources, we need to clean it first. One of the first steps is to calculate accurate energy consumption values for electric vehicles, which is needed because if we used direct measurements of battery levels to calculate energy use, we would get highly inaccurate values. Instead, we take real-time current and voltage measurements and we integrate them over time to calculate accurate energy consumption values. Another important step is mapping recorded vehicle locations to accurate street-level locations. This step is absolutely crucial because locations for vehicles are based on GPS measurements, which are inherently noisy. In order to map those accurate street-level locations, a process which we can see in the images on top, we take a set of vehicle locations from the same vehicle, and in order to map one of them to an accurate street-level location, we consider the preceding as well as the following few measurements. Even though all of these measurements by themselves are noisy, in combination, we can use them to infer very accurate vehicle locations, which we have checked by simulating GPS noise and verifying that our mapping does indeed match ground truth locations. Once we have mapped our locations to accurate street-level locations, we can combine the data set with street-level features such as the type of road or speed limits, which we obtain from OpenStreetMaps. Then we generate a set of samples by segmenting the time series into disjoint contiguous samples based on road segments. Once we have generated these clean samples from our vehicle location data, we join them with a variety of other sources, including high accuracy elevation data obtained from LiDAR, as well as historical averages of weather and traffic conditions obtained from dark sky and heat maps, which we use as substitutes for forecasted weather and traffic conditions. Finally, we split these samples into training and test sets, and we use a number of machine learning models to train and evaluate. We have experimented with machine learning models including simple linear regression, decision trees, as well as state-of-the-art deep neural networks. For deep neural networks, we have explored a variety of network architectures to find the ones that are optimal. Interestingly, we have found that different network architectures work better for electric and different network architectures work better for diesel vehicles. Once we have established our machine learning models, we can train them on the training set and evaluate them on the test set to see how accurately we can predict energy usage. We have trained and evaluated our machine learning models on 3 months of data collected from 6 vehicles, including both diesel and hybrid buses. We will extend the training and evaluation to larger data sets as they become available through our ongoing data collection. One of the key questions that we studied is which factors are the most useful for predicting energy use. In these figures, you can see prediction errors of deep neural networks with better traffic and elevation features, as well as with their combinations. The vertical axis shows the error in the prediction. In this case, lower values mean more accurate predictions. The horizontal axis shows different combinations of features, starting with using only weather features, using only traffic features, using only elevation change feature, using both traffic and elevation, as well as using all features combined. As you can see, weather features are the least useful for both diesel and electric vehicles. These result in the highest prediction error when used only by themselves. On the other hand, elevation features are useful for both types of vehicles. Elevation features by themselves can reduce the prediction error, as well as they reduce prediction error when combined with traffic. The most interesting observation here is that traffic features, on the other hand, are significant for diesel vehicles, but not for electric ones. We believe that this difference is explained by regenerative braking. Basically, for electric vehicles, traffic is not a significant factor because frequent stops due to traffic have a lower energy impact due to regenerative braking. We have also verified that our predictors do not have any systematic error. Specifically, we have verified that the relative error of prediction decreases with the length of transit trips. In the figures on top, you can see prediction errors of neural networks, decision trees, and linear regression models for transit trips of varying lengths. Note that the prediction error is expressed as a fraction of the actual observed energy use, not as an absolute value in this case. This, of course, means that you can see immediately by comparing the values that diesel vehicles are much more easy to predict. The relative error is about half as much as for electric vehicles. Further, as you can see, the longer the trip, the lower the relative prediction error, which means that our predictors do not have any systematic error, and they are well suited for large-scale, long-term planning purposes. We can also see that neural networks generally perform as well or better than other machine learning models. In the figures below, you can see prediction errors of neural networks with various weather features, as well as their combinations. These are similar to the figures that we have seen on the previous slide. Interestingly, we have found that some weather features are not necessarily useful. In some cases, they can lead to overfitting in training. This is something that we'll investigate further with larger data sets. These predictors enable us to evaluate an operational plan in terms of its energy usage. Building on this capability, we have developed algorithms for optimizing trip assignments and charging schedules for mixed fleets of electric and internal combustion transit vehicles to help transit agencies with minimizing the energy costs and environmental impact. Specifically, building on our energy usage predictors, we have formulated and solved the problem of optimizing transit operations for fixed route services where the transit routes and schedules are determined by the agency based on ridership demand. So in a nutshell, we don't consider the problem of selecting routes because we assume that those are determined based on ridership demand. To minimize energy use, we must optimize the allocation of vehicles to transit trips, since our data shows that different types of vehicles are better suited for different trips. Further, we must also optimize the charging schedule of electric vehicles, since battery capacities are limited and electric costs can vary throughout the day. We formulated these optimization problems mathematically. Now, unfortunately, these problems are very challenging computationally due to the large exponential number of vehicle assignments and charging schedules, as well as the large number of constraints, including trip schedules and vehicle travel times. So we have explored a range of algorithms for solving these problems. First, we introduced integer programs, which can find optimal solutions, but do not scale well, and can be applied only to smaller transit networks. We primarily use these integer programs to evaluate how well the other algorithms work on smaller problem instances. Then we have designed heuristic and meta-heuristic algorithms, which are much more efficient computationally, but do not necessarily find an optimal solution. First, we have designed a greedy algorithm, which is very efficient computationally, and produces comparatively the least good results. Second, we have designed a meta-heuristic simulated annealing algorithm, which is a random search algorithm that takes much more computational power than the greedy algorithm, but can significantly improve upon the output of the greedy algorithm. We have evaluated our algorithms in terms of both computational performance as well as energy cost. The figure on the left shows the running times of our heuristic algorithms as well as the integer program. Note that there is a logarithmic scale on the vertical axis. You can see on the horizontal axis different problem instance sizes. We have basically selected a number of bus lines from the Carta schedule, which enables us to check how well our algorithms perform with varying sizes of transit schedules, ranging from only 1 bus line to 12 bus lines. As you can see, greedy algorithm is by far the most efficient, taking only a couple of seconds even for 12 bus lines. On the other hand, simulated annealing can take on the order of magnitude of minutes for 12 bus lines and may take much longer for larger transit networks. However, both of these algorithms are generally scalable. The running time does not increase much as we increase the size of the problem instance. Meanwhile, the integer program, which provides optimal solutions, does not scale well, and for problem instances above the size of 9, 10, it is basically impossible to solve the integer program, even with a supercomputer. The figure on the right evaluates our algorithms in terms of energy cost. These costs are based on Carta's prices for diesel and for electric energy. You can see that our heuristic algorithms, the greedy and simulated annealing, do not perform as well as the integer program, which is optimal, but their performance is quite close. And as you can see, the gap between the optimal solution, the integer program, and our heuristics decreases as the problem size increases, which suggests that for larger problem sizes, the solutions output by our heuristic algorithms can be even closer to being optimal. We have also evaluated our algorithms on the complete schedule of Carta, including all the bus lines served in the city of Chattanooga. This figure shows the energy usage of transit assignments found by our algorithms, as well as the real assignments used by Carta. The figure is based on a number of different days, so we can see how well our algorithm performs on different instances of the problem. We find that both energy costs and environmental impact can be lowered through our assignment algorithms, which means that we can lower these just by changing the assignments and charging schedules. Overall, we estimate that through optimization of transit vehicle assignments and charging schedules, we could save around $48K in energy costs and about 175 tons of CO2 emissions annually. Next, I would like to give an overview of some interesting supporting results. The macroscopic model previously introduced has good applications on transit route planning and fleet management. However, there is another type of vehicle energy prediction model called microscopic, which has applications in vehicle driving trajectory optimization, such as at signalized intersections or driving cycle analysis for energy consumption estimation. Microscopic models will predict fuel or energy consumption of a vehicle at every second of driving. Currently, there are several vehicle powertrain simulation models that are developed by universities and the Department of Energy National Laboratories, such as Autonomy by ANL, FastSim by NREL. These powertrain simulation models are usually developed for specific vehicle models, and they usually require detailed attribute information of the vehicle they are modeling, such as aerodynamic coefficients, transmission efficiency, and so on. Since we have all of this data, we develop a non-parametric data-driven microscopic energy prediction model for electric buses. This will help future users to apply our model without the burden to provide vehicle attribute parameter information. When predicting energy consumption of the electric bus at the per second level, there are many factors. Specifically, there are different driving conditions. So in developing the microscopic energy prediction model, we must first classify the vehicle and energy data into different driving conditions based on acceleration rate. Based on lots of experiments, we found it is best to divide the data into 3 driving conditions and then develop one prediction model for each one of these conditions. The 3 conditions are acceleration, cruise driving, and deceleration. The input variables for the prediction are speed, acceleration, road grade, and meteorology information, which are humidity and temperature. For each neural network, we conducted variable and model selection to identify the model setup that attains optimal prediction performance. Our data-driven neural network models show better prediction performance than regular linear regression models developed in previous studies. The lower right figure shows prediction performance on trips, where the red line is the cumulative actual energy consumption and the blue line is the predicted consumption. To help practitioners use our data analysis and optimization algorithms, we have been developing a visualization framework using state-of-the-art web technologies such as HoloViz and Kepler-Geo from Uber. This framework is accessible programmatically using Python notebooks for data scientists, for example, and it also allows the creation of archival dashboards as well as live query websites, which I have shown earlier in the presentation. Here you can see an example of the visualization interface that produces an analysis map from the recorded energy usage data. The figure on the left shows the energy consumption of BYD electric vehicles during the early morning, while the figure on the right shows energy consumption on the same routes during the afternoon. As you can see, energy consumption depends on both the route as well as the time of the day. This project has had influential results for CARTA as a transit agency by creating a data framework that will enable CARTA to make informed decisions in terms of vehicle allocation as well as capital investment. These decisions are important since there is still a substantial gap in the capital acquisition costs between electric and diesel buses. Understanding the true energy costs and benefits of vehicle deployment is critical to reducing operational costs and environmental impact. Ultimately, improved transit operations lead to improvements in service to the community, since energy savings and cost effectiveness translate directly into the agency's ability to enhance operations. Finally, I would like to mention some related projects from our team. The first project is another Department of Energy funded project on optimizing the energy use of transit agencies. The goal of this project is to use artificial intelligence to optimize an integrated fixed route and on-demand transit service. The advantage of this integration is to combine the complementary advantages of fixed route services and on-demand services. Fixed route services tend to be more energy efficient, however, they tend to cover less area than a flexible on-demand service. On the other hand, while on-demand services can cover larger areas, they tend to be less energy efficient. Our idea is to use artificial intelligence techniques to optimize these kind of services together, creating a more efficient integrated service. In order to do that, we are using state-of-the-art artificial intelligence techniques such as deep reinforcement learning and Monte Carlo tree search. We're also working on an SF-funded project whose goal is to design a community-centric microtransit service. This project focuses on a community-centric approach, and our team includes multiple social scientists who will help us with the community outreach in order to design a microtransit service that focuses on the passengers. Ultimately, our goal in this project is to make a positive impact on the community by providing a more accessible and more affordable transit service. Finally, in response to the ongoing COVID-19 epidemic, we're also working on another NSF-funded project whose goal is to help transit agencies to serve the fluctuated demand due to COVID-19 with the reduced capacity due to the countermeasures such as social distancing. This is another collaboration with the transit agency CARTA as well as the public transit agency of Nashville, Tennessee. If you're interested in more details about this project, please feel free to reach out to me or other PIs on the project, or visit our website, smarttransit.ai. I would like to thank you all for your attention. If you have any questions, I will be very happy to answer them right now. And again, I would like to encourage you to visit our website, smarttransit.ai, where you can find more content, including datasets, publications, and code.
Thank you for that wonderful presentation, Dr. Laszka. We will now open up the floor to any questions the audience may have. And to do this, we ask that you post your questions in the chat box located at the bottom of your screen. All right, and so we had a question earlier from Alan Rossiter. He asked, you quote that energy efficiency is in kilowatts per mile. However, a kilowatt of electricity is not a kilowatt of diesel. How do you adjust for this?
Hi, thank you. Yes, so that's a good question. We use standard conversion rates. I can give a reference. We use standard conversion rates from gallon of fuel, diesel to kilowatt hour energy.
All right, and there's another question from Dr. Krishnamurthy. He asked, how scalable is this model? And based on the cost of collecting data and the method development and interventions, what is your estimate of the return on investment? And further, can you estimate the cost per ton of CO2 avoided by the application of this technology?
So regarding scalability, could you please clarify, do you mean the optimization or the energy usage prediction?
The optimization routine.
Optimization, thank you. Yes, that's a very important concern. The problem is computationally very challenging. So we know that it's impossible to find optimal solutions in a scalable way. That's the reason why we're proposing heuristic, meta-heuristic approaches. Those are very scalable. We can easily run them for the full schedule of Carta, and we could scale them up for larger transit agencies as well. We're actually actively working on improving those algorithms. We have improved results compared to what I presented actually in terms of solution quality. And I think the second part of the question was regarding return on investment. So that kind of depends on what you need to invest in order to do this. The optimization relies on energy usage estimates. Now, if you have some just coarse estimates, that can work as well. Essentially, the better estimates you have to start with the optimization, the better results you get. In general, you could just, for instance, use prediction results that we have obtained for vehicles in our study, and those should be to some extent transferable to other vehicles as well. Or you can use other existing prediction models for vehicles. And then the optimization problem itself doesn't really require any investment. As long as you have your transit scheduling in some standard format, the algorithm should be able to output an assignment.
And there was a further question, or a question on top of that. It says, can you estimate the cost per ton of CO2 avoided by the application of the technology?
Cost per CO2? I'm not quite sure. Does the question ask about monetary cost of?
Yeah, the cost per CO2.
Avoiding CO2 generation, right? And it costs you certain amount of money to create all these algorithms and to collect the data and for you to have this particular system. So I'm asking you to estimate what the cost per ton of CO2 avoided is. Because, for instance, if I were to just release the CO2 and capture it by direct air capture, it'd be $600 a ton. Right? So that's what I'm trying to compare to.
Mm-hmm. Yes. So now that we have already developed and implemented this, it depends on the transit agency, but I would say that the investment is really minimal. Again, for the algorithms, you really don't need anything other than transit schedule in a standard format like GTFS. And at the end of the day, compared to the CO2 emission, a negligible amount of energy used for the computation itself. And as far as for the prediction and data collection, that again, to a large extent, depends on the transit agency. Some agencies already have telemetry devices in place, and then those can be easily hooked up with our framework, which again is already developed. Other transit agencies that don't have telemetry devices and don't want to invest in them, they can essentially rely on data collected from vehicles in other fleets.
So Christine's asking, can point-to-point transition like Uber or Lyft be similarly analyzed?
Yes, that's actually what we're working on right now. I mentioned in the end a couple other projects. The two bigger projects that we're working on from DOE and SF both include micro-transit solutions, for instance, paratransit, but we're also considering on-demand shuttles, which work very similarly to how Uber and Lyft does. These are on-demand services with relatively small capacity vehicles. And our goal is to collect, again, data from these vehicles to try to predict the energy usage and then optimize them using artificial intelligence.
And then another question. So Houston is doing the electric fleets for buses. Do you think that this study is replicable in the inner loop as well as like the greater Houston area, connecting all the bus systems together?
Yes, I would say it is. Again, it depends on exactly what kind of data sources are available. But our framework is flexible enough that I think most transit agencies would be able to adopt it.
So another question from Alan, he's saying, or he's asking that the transit agency is also reducing operating cost so that the cost per ton of CO2 is probably in the negative area. Is that correct?
Yes, so at the end of the day, really what we're trying to do is reduce fuel and energy usage. And that directly translates into reducing expenses spent on fuel and energy. So that there's actually a very easily quantifiable dollar value saving for the transit agencies if they optimize their assignments.
All right, thank you. Does anyone have any other questions that they would like to have answered? All right, well, so if there are no more further questions, we can probably go back to the PowerPoint. All right, so once again, I want to say a big thank you to Dr. Laszka for having such a great and informative presentation, as well as our partner Evolve Houston and everyone in the audience for attending this event and making it possible. So please join us next time for the electric vehicle webinar on December 10th, 2020 from 1 p.m. to 2 p.m. And Dr. Yan Yao will discuss the next generation batteries for electric vehicles and their stationary storage. So once again, thank you very much and have a great rest of your day.
Thank you for the opportunity, and thanks everyone for your attention.